All right, so today we are mainly looking at chemistry, and this is one of the topics of the part of chemistry which is normally called analytical chemistry, especially at varsity level. But at our level, we start by looking at what you call stoichiometry. And the term stoichiometry is actually coming from the Greek term, which stands for stoichion and metron. Stoichion stands for the measure, or rather quantities, and then metron stands for the measurement. So basically, when we're looking at stoichiometry, we're looking at the measurement of quantities. Now, we ought to give a lot of credit to quite a number of chemists who actually came up with a lot of experiments that led to calculations. So we've got one of them being Avogadro, who came up with these constant, which is 6.2, what's the value? 6.02 times 10 to the power 23. So that constant is normally given, but you shouldn't worry about remembering it. And it's basically made to calculate the number of either particles or molecules, depending on what you are given. Now, it's divided into, stoichiometry can actually be divided into three sections, depending on how you're looking at it. The first part basically looks at the abundance of elements, how you can calculate the percentage mass, and also calculate the value of that particular element. So we know that some of the elements, especially those that are in our periodic table, they are natural elements which are neutral, and their abundance is 100% mainly in nature. So for instance, if you look at carbon, which is the main element that we normally compare other elements to. So which is why when you look at the relative mass, you can either look at the relative atomic mass or the relative molar mass. Now, when you're looking at the relative atomic mass, this is basically on an individual element. For instance, in the periodic table, if you've got hydrogen, you've got carbon, you've got oxygen, you've got fluorine, and any other. So in that case, we'll be looking at the relative atomic mass. Now, as I've already mentioned, most or all of those elements that are in the periodic table, they have an abundance of 100%. So for instance, if you look at magnesium is, if you look at the periodic table, I believe it's 24. So that nucleon number, or the atomic mass, will be that relative atomic mass. So these will be the individual elements. Then if you look at the molar mass now these will mainly be the compounds. So the molar mass, you can have, it's divided into two. You call it the relative molar mass and also the relative formula mass. Now, when you're looking at the relative molecular mass, basically, not the molar mass, but the relative molecular mass, you're looking at covalent compounds now. Covalent compounds. Then the RFM, because these are not molecules, but they are ionic compounds, so we call them the relative formula mass. So covalent, and this is ionic compounds. Now, I've highlighted that we ought to give some credit to Avogadro. He came up with this equation. So this is the equation that we use mainly for the calculation of the number of elements, the number of particles that is in an element. Then if you're looking at a molecule, or a compound, that is where we'll be looking at the number of molecules. For instance, if you've got oxygen is a molecule. So in that case, we'll be looking at the number of those. So I'll give some examples on how we can calculate that. And then of course, we've got the molar volume. The molar volume, it was calculated through experimentation that it is relative to 24 cubic decimeters. And then we also have concentration, which is the ratio of mainly the number of moles per unit volume. But you can also have even the mass per unit volume. So you can have grams per cubic decimeter, but we normally use mole per cubic decimeter. That's the main unit that you'll use for concentration. So for starters, if you are asked to calculate the molecular mass, for instance, we are given, let me look at a simple one. Calculate the molecular mass of hydrogen chloride or hydrochloric acid. So you'll notice that to calculate the MR of this, you will need the AR of hydrogen, which is 1, and you'll also need the AR for the chloride atom or a chlorine atom. So for the chlorine atom, which is 85.5, I believe, in the periodic table. So the MR will be 1 plus 35.5. So this will give us 86.5 grams per mole. So once it has the units, you will notice that it is the molar mass. But if it is the relative formula mass, that one you will not have the units because it's relative, or even the relative molecular mass. But if it is the molar mass, you will always have units. Now, why is this important? This is important because you can be asked to use this in order to calculate the number of moles. Now, specifically, if you are given an equation where you can compare the reactants together with the products, I'll show that one later as well. So let's say now, in the mole concept, so this is just a simple example of how we can calculate the molar mass. So the RFM you can also calculate. Maybe let me also give another example. The RFM, now usually this would be for an ionic compound, let's say calcium oxide, RFM of calcium oxide. You will notice that from ionic bonding, calcium is, as a cation, is 2 plus, and oxygen is an anion, is 2 minus. So calcium oxide is a formula, a chemical formula of CaO. Now, this will be equivalent to the AR of calcium, which I believe is 40, plus the AR of oxygen atom, so which will be 60. So the RFM will be 56. Now notice I do not have units because it's the relative formula mass. Now, we do have an important formula which relates moles and mass and molar mass. It's a very important formula. It is called the molar mass equation. So the molar mass equation, and I'm also going to show how it relates to the number of particles or the number of molecules. So the molar mass formula says the number of moles will be equivalent to the mass divided by the molar mass. So this formula is very important to remember. Now, one way of remembering this, it is to understand that the units actually for molar mass is what? Is grams per mole. So because the molar mass is grams per mole, that means if you want to find the MR, oh, actually, I converted it wrongly. So the molar mass equation is actually taken from, so grams per mole, MR is equals to M over N. So which means if I want the number of moles, I will multiply both sides, so it will be M over MR. In fact, I have written it correctly maybe the last time. So I wanted to show, we see, where you see MR being M over N. It is because Bugalama units, the MR is grams is the numerator, then mole is the denominator. So MR is equals to M over N. And also notice the M should always be a small letter, because once over a capital letter, that's molarity, which is also equivalent to concentration. But again, 7 is the small letters. Now, why is this important? As you see, using the same MR of hydrogen chloride, we are told, we've got 30 grams of hydrogen chloride, normally hydrochloric acid. Basically, about to calculate the number of moles of the 30 grams. So what is the number of moles? What is N? The number of moles. So what you will do, you will have to start by calculating the MR, in which we have calculated by looking at the MR of hydrochloric acid or hydrogen chloride. So that was in 36.5. Then, because you want to find the number of moles, that's again, N is equals to M over MR. So this will give us, where there is the mass, you substitute 30. I will put the units so that I show what's the atau cancelana basic moles. So MR will be 36.5 grams per mole. So mathematically, 30 divided by 36.5, G cancels G. Low mole, because we have 1 over mole, now divide a fraction is the same as multiplying its reciprocal. So this will give us, well, let's have a calculator start see. The answer will give you lemma moles. So let's see how we calculate this. Is this your bag or? No. Oh yes. So you will notice that yes, so 30 divided by 36.5, this will give you 0.82. So let's on a calculator because it's not exact. So 0.82191780. Then to 3 significant figures, it's 0.822 moles. So these are the moles of hydrogen chloride in 30 grams of hydrogen chloride or hydrochloric acid. Now, how many, because this is a compound, it will not be particles, but it will be molecules. So find now the number of molecules in hydrogen chloride. So the number of molecules, so this is Avogadro's number of this equation. Let's see capital letter N, which is the number of particles or number of molecules, is equivalent to the number of moles. So the number of moles is 0.822, then multiplied by 6.02 times 10 to the power 23. Is it? Which are Avogadro's number, if I recall. Yes. Then guess where I multiply 0.822, usual, but I'm going periodic table. I'm just recalling it from my head. Times 6.02. Now we're going to buy again. Okay, this one fortunately is quite easy. 4.94844 times 10 to the power 23. Now, this is the number in full, but you still need to kill any exact molecules. So this will be the answer. Because it's exact, we don't need to round it up. So this is how you notice from that I've actually solved the two problems using one concept or using no. I've solved two concepts using one example. The first concept was to calculate a number of moles using the molar mass equation. Then using Avogadro's number and the equation for the number of particles to get the number of molecules. We have to even point here from here because hydrogen chloride in a liquid form, we can also have a concentration, like you can form dilute hydrochloric acid because it's a strong acid in a liquid form. Now calculate as E concentration. So let's say still la hydrogen chloride, or let's call it now hydrochloric acid, in a 20 or 30 grams of HCl in 20 cubic centimeter solution. Yeah, let me put it like this. So calculate the concentration of 30 grams of hydrochloric acid in 20 cubic centimeter solution. Kusho ukuthini lo? Kusho ukuthi ngakha i-concentration ndawo 30 grams of hydrochloric acid in 20 low distilled water. So now so fagile kwakhe concentration le ngba ngiyo reference calculator. So you notice ukuthi number 1, so C is equals to N over B. Yile site yona okay, sifuna na concentration. Yile site wona. Noma yile sinike kubona. Notice ukuthi siniketwe 9 to 30 grams of hydrochloric acid. Sinamconverter into moles. Low 20 cubic centimeters low distilled water, which we are going to put love volume. So which means the step sector, it is to convert these 30 grams into moles. Sigwenda jando, 70 mR. So the mR would be the mass over mR is equal to M over N, and it's in a square N. So now N, so times N times N. So actually N is equal to M over mR. So the mass, 30 grams, bese i-MR ngo-36.5 sike samthola ngale. Remember, AR of chlorine atom is 35.5. AR of hydrogen atom is 1. So now also have 36.5. So now divide that up. Again, you get that answer that we got. I believe it was 0.1. 822. 80 divided by 36.5. 80 divided by 36.5. Yes, scroll again. 8.0.821917.807. So we should be 0.822 moles. So now regular moles are 30 grams for hydrochloric acid. So you will then take the moles down and just need to calculate the concentration. So 0.822. Now you will notice we are not able to divide them at 20 cubic centimeters. Why is this wrong? It does you get to my unit of concentration. Moles per. Give me what you call it. My units. Cubic decimeters. Cubic decimeters. Inkinga lesinayo lana yini? Yabona ngilethe ma cubic centimeters. Now ufune sathi ke na conversion, let's see, 1 cubic decimeter is equals to 1,000 cubic centimeters, noma ke 1,000 milliliters. So 1 milliliter is actually equivalent to 1 cubic centimeter. But 1,000 cubic decimeters, no, rather 1,000 cubic centimeters is equivalent